Welcome to our Viewpoints. I'm your host, Brian Fuller, and today we're joined by Jeff Wittich, Chief Product Officer from Ampere Computing. Ampere was founded in 2018 by Renee James, a former Intel president, who had a bold vision: revolutionize data center computing using the ARM architecture. In this episode, we explore how Ampere is addressing the mounting challenges of power consumption and performance in modern computing environments from edge to cloud, the origins of Ampere and its strategic decision to build ARM-based processors for data centers, how generative AI has impacted Ampere's approach to processor design and the distinct requirements of AI training versus inference, the evolution of edge computing and why certain AI workloads are naturally gravitating towards edge deployment, Ampere's product strategy, including innovations in chiplet architecture and AI acceleration, a real-world case study of Spacetech's implementation of Ampere processors for edge AI applications, and much, much more. So, now we bring you Jeff Wittich. So, Jeff, welcome. Thanks for taking the time.
Yeah, glad to be here. Thank you very much.
Catch us up, if you will, on Ampere, which burst onto the scene. I don't think that's too hyperbolic in 2018, right? You, Renee, came out of Intel, and we're gonna attack this particular market, but not with an x86 device. We're gonna attack it with the ARM architecture. Take us back there briefly, and then bring us up to speed where you guys are today.
All right, perfect. Yeah, you're right. Especially in CPU timescale, 6 years is nothing. So you're right. We did kind of burst onto the scene 6 years ago, and we've done a lot since then. So kind of to go back to 2018, 2019, what our real vision was. When we looked out across the data center landscape, we saw a couple of key challenges that were emerging. One was power. It wasn't as obvious 6-7 years ago that this was going to be a massive constraint. To put it in perspective, for about 15 years there, the total power consumption in the US never went up. We had many, many years of very consistent power consumption. And so there was always spare power on the grid. And that was because we had created all kinds of efficient ways to reduce the amount of power, even while new usages were coming online. Well, a couple of things were starting to change. One, vehicles were electrifying. That's a really good thing, right? Takes things away from using fossil fuels in our vehicles, but it also does mean that there's an increased demand on the grid. And the second thing is that there were factors that were making it clear that data center power consumption could start to increase, even though it hadn't increased for a long time. The things that were happening there were, workloads were starting to change. Workloads were becoming more and more compute intensive as analytics workloads got more sophisticated, as the AI workloads of the time, which were more computer vision and recommender model focused, even those workloads were getting more sophisticated. Obviously, since then, we've seen Gen AI and LLMs really just ratchet that up by another order of magnitude. So workloads were getting more compute intensive. We'd already kind of used up the easy power efficiency gains. Data centers are already very, very power efficient. The most efficient data centers in the world maybe only have 5 or 10% waste. And that's a change. That maybe used to be 50% waste, 60% waste a decade ago. So great job making data centers more power efficient, but it also means there's only 10% more to go and attack. There's almost no inefficiencies left there. So we did a great job there. And then also just the x86 CPUs at the time, they weren't increasing in efficiency. They were increasing modestly in performance gen over gen, but oftentimes that performance gain came with the exact same gain in power. So performance per watt just wasn't increasing. What that meant was that each generation at the rack level, even though each CPU had more performance, the performance at the rack level wasn't going up. It just meant that every single year, when you put the new generation of, I'll just say Intel CPUs in there, it meant that you had less CPUs in the rack, but the same exact performance that you had the year before, consuming the same amount of power. So it wasn't helping anybody create more dense or higher performance data centers. And so we looked out across the landscape and we said, there's a clear opportunity here. The scale of compute continues to increase. The cloud is obviously the model of computing that everybody's migrated to, whether it's on-prem or public cloud or hybrid, it doesn't really matter. It's a cloud-based model, which is big compute at scale. And there were clear problems that were going to make it difficult to keep scaling the cloud if the industry didn't have other solutions. So that's where Ampere came about, is we decided there had to be a better way to deliver high performance compute and not deliver high performance compute that was also very, very high power. There was a way to go in and re-architect things from the very most base level and build something that was high performance, but also very low power and power efficient. And that's where we came in. And so we, started with a very different approach than the x86 vendors. We started with ARM-based CPUs, and really innovating all the way down to the architecture and microarchitectural level to build something that was really well suited for the cloud environment of today versus the legacy environments that those x86 CPUs were built for when they were first built 10, 20, 30 years ago. So that was really the impetus, and we've done a lot in the meantime.
You mentioned a couple of the prevailing workloads then when the company was launched around Vision. Generative AI literally exploded on the scene 2 years ago. Has that had an impact on how you think about building solutions, or is your CPU forward approach just naturally fit into the evolving demands of Gen AI?
Yeah, I think there's two elements of it. I think at a strategic level, it doesn't change a whole lot because Gen AI really just made those strategic imperatives more important. The idea that you need more and more performance, but you can't consume more power to do so, or you're going to run into some real constraints. So it fits into the exact same space. And obviously, building a general purpose CPU means that you're building for a lot of workloads. Now, 5-6 years ago, the workloads that I cared the most about it was web servers, it was databases, it was video encoding. It was AI inference, but it was AI inference in terms of computer vision or natural language processing. It was recommender models, non-transformer based AI models. But that was a big focus for us back then. What's changed is that the balance of workloads has changed a little bit. And so a higher percentage of the workloads are now AI inference than before. And the nature of those AI inference workloads has changed a bit, with the transformer-based approach and the LLMs that came from that. What it means is the models are much larger than they used to be. And some of the compute elements that are best utilized for them look a little bit different than what the compute elements looked like for the models of the past. Now, the good thing is that's what a general purpose CPU is really good at. It's really good at being really versatile. So as workloads change, it does a pretty good job at virtually any workload. But since we knew that AI inference had the possibility to be one of the predominant workloads in the future, we did do specific things to ensure that AI inference as a workload ran really well on our processor. Things like ensuring that all the numerical formats that people care about are natively supported. So things like bfloat 16 or int 8. We did a lot of work on just ensuring that the performance of the hardware itself could be exposed really easily to the end user. So about 3 years ago, we acquired a company on Specta that was building software acceleration libraries for AI inference. And the result of that was that it became very, very easy for people to run AI inference on our CPU and to harness the SIMD units and the other microarchitectural elements of our processor that are really good at AI inference to really get the maximum possible performance out of those without the end user needing to actually do anything to optimize their code or optimize their model or worry about whether the framework, all that stuff just happens under the hood. I would say that we foresaw some elements of this. I can't say that I could have predicted exactly where we were going to end up today with these LLMs, but you could see what direction things were going. And so you could start to build things into the CPU and then build the ecosystem around it so that it was as easy to run AI inference as any other workload on these processors. Now, that being said, as we look at the very, very largest models, as we get out into the multi-hundred billion parameter models, the trillion parameter models that'll soon come, at that point, that does require some additional processing elements within the SoC. And that's why we announced a couple months ago our Ampere 1 Aurora line, which still uses the goodness of our really efficient general purpose cores, but then adds in some acceleration elements, not in the cores themselves, because you don't necessarily want to burden the cores with these types of compute elements, but tightly coupled to the cores across the mesh within the SoC. So you get that low latency, but you also have a lot of flexibility with how you scale those compute elements. And you don't have to make a lot of trade-offs between whether you want to optimize for general purpose or AI inference at any given moment, given that our customers don't know that. And they will always have to be able to balance between the two of them. So I think that the details have changed. The tactics change over time as the workloads have changed, but the strategy isn't different. The strategy is still really high performance at really low power across a flexible set of workloads, like always ran in the cloud. Those workloads just change. And that means that the compute changes with it over time. And if you can build a really flexible platform that's able to easily change over time, integrate things into it that become general purpose over time, then you have a big advantage.
I have so many forward-looking questions for you, but we'll get to those. Right now, at this time slice, this is a perfect question to ask of the product guru. What are the challenges around workloads and solution implementations that you're hearing from customers and developers out there, and how is Ampere addressing these?
Yeah, I think that there's a couple elements to that. One is that a lot of these solutions are very, very complex today to implement. The solutions look at the platform level, look a bit different at times than the solutions at the platform level that existed a couple of years ago. There's a lot more elements. System level optimization is a lot more important than maybe it was a couple of years ago because of the amount of data traffic, the movement between different elements within the server. One thing that we're doing there is about a year ago, we created the AI Platform Alliance. The idea here was there's a lot of people out there that are building really, really cool elements that can go into a overall AI solution. We're building a CPU. There's people that are building accelerators that are really good at, maybe it's different types of models, different size models, different deployment models. So a wide variety of accelerators out there. Also, there's a wide variety of ISVs that are building their own frameworks that maybe sit on top of some of the other AI pieces to make it easy for enterprises to deploy at a higher level. You have SIs, OEMs that are building a wide variety of systems that may look very different than the systems that people were deploying a couple of years ago. So it's complex. There's a lot of different players in this market, and the solutions look really complex from an end user perspective. So it can be easy to just default to the status quo, whatever the known quantity is. So we created this AI Platform Alliance so that we could bring all those folks together, collaborate on how our solutions work together, and then build a set of solutions that are easy to deploy for, say, an enterprise AI user for a specific use case without them needing to piece the entire solution together themselves. So easy to deploy solutions. Like, for instance, we built a solution with NetInt. NetInt has their video processing units. So you think of a use case like Whisper. So using Whisper for, say, doing transcoding or translation and transcription of live video, for instance, like a newscast. You want to close caption it. Maybe you want to close caption it in 30 different languages. Well, Whisper does a great job of that. And so when you take a overall solution that has NetInt's VPUs and our general purpose CPUs, and then you build it out at the platform level with someone like Supermicro, now you have almost an appliance that somebody could deploy. So if you're a broadcaster, you have a box that does exactly what you want, that's going to be able to, say, process hundreds of video streams simultaneously and translate and transcript them real time. And you don't have to worry about piecing this together yourself. And so that's one of the things that we're helping to address, is just the complexity of the solutions is very high because we are in the early stages still of this AI cycle. It may seem like we're far into it. Depends on kind of, I guess, where people have been and their place in the industry over the last 5 or 10, 15 years. But we're still really early in this AI cycle. And so we're dealing with a lot of nascent technologies and solutions that are just coming together, real time. So that's the AI Platform Alliance helps address that issue. The other issue is just, again, it goes back to the power issue. There's suddenly potentially extra more increase in compute demand, but we didn't suddenly get more power in these edge locations. You're still constrained to maybe 100 watts. Your big data center is still constrained to whatever the power capacity got off the grid. In 5 or 10 years, that can change. Obviously, we see people going in and looking to spin up nuclear reactors again and things like that. But that doesn't happen overnight. That's not a next week type of thing. We still have a big build out that's going to occur before all that stuff comes online. And while we're doing all that and bringing that online, the compute demand's going to keep going up and going up and going up. So we need to do everything we can. We need more power sources. We need cleaner power sources. We need more efficient data centers. We need more efficient processors. We need more efficient solutions. We need all of that stuff to come together. And I think that along with the power challenge, the thermal challenge is difficult too. There's a lot of cool, innovative technologies out there, direct liquid cooling, immersive cooling. Some are more practical than others, and they can be really efficient. But if you have a data center that you just built a couple of years ago, and when you built it, you were planning for a 10, 15, 20-year life cycle, you weren't planning on going in and retrofitting the whole thing in a couple of years. You have what you have. You have the investment that you made. These data centers live over a very long lifetime, and it's not trivial to go in and gut them or completely overhaul the architecture of them or redesign the way the racks are laid out or create new power and cooling delivery systems. Those don't happen overnight. And it's important that we deliver solutions that can be deployable today everywhere at scale, and not just solutions that eventually will be able to be deployed everywhere at scale in 5 or 10 years. So those are some of the problems that we're helping people to solve today, is just make things simpler, help them fit into their existing environments today, because that not everything can change overnight, and build a path to the future with these customers. And I guess as enterprises are coming online and running more and more AI workloads, and more of those AI workloads are very, very critical to them, and they want to have some control over where and how they run them, it just magnifies the problem a little bit more, because this isn't just a couple of people, big hyperscalers running AI workloads. This is hundreds, thousands, tens of thousands of enterprises where AI is now a critical workload, and they have to figure out how to adopt this at scale as well.
So the crown jewels at this point are Ampere 1 and Ampere Aurora. Give us a compare contrast. And somewhere in my research, now I can't find it in my questions, you're enabling fanless designs, I think. Is that right?
We are, yeah. So when you look at it, Ampere 1 is our flagship product today. General purpose compute. Today, the CPUs have 192 cores. We'll be releasing a 256 core CPU soon. And that's really what we see as the workhorse within the data center space, but also out into the edge. So really efficient processors, can run any workload you throw at it. And that solves the bulk of the data center problem. And you mentioned the fanless designs. Again, the type of efficiency that we're delivering in the data centers equally applies out to the edge, just, different scale. Maybe instead of a 500 watt server, now we're talking about a 50 or 100 watt device that's sitting out at the edge somewhere. And some of those devices do need to be fanless. A good example of one of these is we have a deployment in space today. Fans don't work in space. Space is a vacuum. So a fan does no good in space. There's no airflow in space. And so those are devices that have to be passively cooled, because you don't have any way to actively move air, or, a liquid's not feasible in that environment either. And so, yeah, we're enabling really efficient solutions out there where you can still get a couple dozen cores at 40 watts, which doesn't require any active cooling at all. That's Ampere 1 is, wide range of core counts, wide range of use cases, wide range of power consumed, but always efficient and matched to the environment that people are looking to deploy it in. And then Ampere 1 Aurora is the next step in our product line. It's taking the flexibility that we built into Ampere 1, where we moved to, we have a chiplet approach. We designed our own disaggregation architecture. We designed the die-to-die interfaces and architecture, but we designed them in a way that'd be very, very flexible. Now, the way I would maybe describe it is Ampere 1 uses that flexibility for us to build a bunch of products that are flexible for us to build and to provide to the market. With Ampere 1 Aurora, we take that flexibility and we start to utilize it in different ways. So now that same flexibility that allowed us to use a lot of different chiplets to build general purpose CPUs, you can now use that same type of flexible architecture to now start to drop in AI accelerators that aren't general purpose, but which seamlessly mesh with the general purpose CPU cores. And taking that a step further, it could be anywhere. It doesn't need to be just AI. Now, obviously, that's kind of the killer workload of the moment, and that's where it makes the most sense to go in and apply those resources and build a specific type of accelerator for. But you could build this acceleration in for any type of workload, and this doesn't need to be Ampere developed IP or Ampere developed chiplets either. This can be third-party IP that has been developed by another company. Maybe it's something very unique to their workload or their environment, or maybe it's something that's incredibly sensitive for them where they don't want this IP out there and deployed by other people. So Ampere 1 Aurora kind of takes that flexible framework, and it now really takes general purpose compute to another level, because we've created another way to create that general purpose aspect while also having acceleration. So you kind of don't have to, in a way, you don't have to choose anymore between whether you want something that is general purpose versus something that is domain specific. You can actually have any of that within a flexible set of solutions that can go into the same types of platforms. And so it's really, I think, it's that evolution of compute where maybe general purpose compute has now turned into AI compute. And AI compute is that more broader set of workloads, some of which are very specific and some of which are very general.
You talked earlier about power at the edge, but because you sit in such a unique position, you have great visibility about what's going on at the edge. There's a movement to move more AI compute to the edge, keep it there for reasons of lower latency, for privacy and security. How do you see in the next couple of years that evolving? There are obviously some workloads, I'm thinking video files, that are better suited being computed on in the cloud. But how do you see edge workloads evolving?
Yeah, I definitely see. I definitely see a big movement to the edge, and it's these latency sensitive workloads that tend to drive this. It's why going back 15, 20 years, it's why you started to see CDNs built up for caching some of these videos out at the edge, because you wanted low latency, and you also wanted to minimize some of the data movement as well. So things that are lots of data and big and need to be low latency, those are really well suited to be sitting out at the edge. Now, what limits it sometimes is when the edge doesn't have enough performance, then you make compromises and you move things further away because the source of the large processing is somewhere else. And so I guess that's where we sort of have two competing forces. Workloads that are getting bigger, that are more and more latency sensitive, they're going to want to sit at the edge. And then there's kind of the role we play on the technology side, which is figure out how to deliver as much compute out to the edge at as lowest the lowest power possible, so that the intersection point of those things is as big as possible, so that everything that wants those characteristics of the edge can sit there and doesn't need to go somewhere else for processing. And again, this same type of thing happened over the last 20 years or so. And these workloads find their natural place. I think we had, there were big arguments 20 years ago, 15 years ago about the cloud and where things are going to sit between public cloud and private cloud and edge, and how we were going to create a taxonomy around this and what it was all going to look like. And at the end of the day, the workload needs and the economics of it kind of end up settling it. And there will be a large amount of workloads that if we enable the right technologies, will sit at the edge and will want to be close to the user. And I guess that's our role, is to make sure that we make that feasible and economical. And so I really just, AI is just, again, perfect example of a workload that wants to sit at the edge wherever possible. It has all the characteristics, needs to be low latency, lots and lots of data. Privacy can be an issue. There can be locality issues as well. I mean, there will be places where you'll want to run different models depending on what country you're in or what geo you're in, right? There could be language dependent, it could be policy dependent. And so there'll be a lot of reasons why inferencing is going to scale everywhere. It's going to be the biggest scale out workload that we've ever seen. And that's one thing where I think as we think about AI, I think this conversation has been good in how we talk about inference. What gets lost a lot of times in the bigger picture is all AI gets thrown in together, and training and inference get kind of thrown together. And the key here is that inference and training look incredibly different. So a lot of things I'm saying here about AI inference maybe aren't true for AI training. But we have to look at them, even though from a workflow perspective, you train, then you infer. From a compute perspective, the requirements are very different. And from a deployment perspective, the deployment requirements are very, very specific, and they're going to want different solutions.
Speaking of the edge, Jeff, Ampere has a very interesting use case with Space Tech, which is a Chinese technology company that's part of a larger real estate enterprise. Now, we've covered this in a separate podcast and a case study with Space Tech CEO Sean Ding, and I encourage listeners to go listen to that story because it's amazing. Jeff, tell us about it from your perspective.
We've been working across a pretty wide range of use cases for a while now, everything from cloud out to edge. And the kind of connective tissue is that there's a lot of analytics and AI that occurs in all of those places. And so having a really high performance solution that's also really power efficient matters across that whole spectrum, but for different reasons. In the case of Space Tech, they provide property services for a really large amount of real estate in China. And the challenge that they were facing is that there's just more and more smart devices that are collecting data that's just generating a ton of traffic, but it also opens up a lot of service opportunities. Things like facial and vehicle identification, security services, managing certain assets on the properties like the lifts. So with all that dynamic data coming in and all these opportunities to use that data in a smarter way, they needed a really high performance edge AI server to provide services, along those lines. And so that's sort of where this originated. Was that they were using an existing x86 solution, but they needed something that was higher performance given the change in data traffic and the change in opportunities, the growth in opportunities. But they needed something that was also really power efficient at the same time. And that's where Ampere came into the picture.
Can you share any of the data that has been captured so far as these guys have implemented Ampere solutions?
Yeah, I definitely can. When you look at the workload, there's obviously a lot of elements to the workload, but probably the two most critical pieces of it are video decode, because that's often the data source that they're using. And then the other key element of performance is AI inference to actually generate the results that you're going to take some action on. And their previous solution was an x86-based solution, and it had a discrete GPU in it. And so that's their baseline. And so the key was to deliver much more performance for video decode and for AI inference than that solution, but to still do so in a really power efficient way. When you look at those two elements, the video decode, our processor in this solution was able to decode 126p 25 frame per second video streams in parallel. And so that far exceeded what they were capable of doing with the existing x86 solution. Where it kind of comes full circle then is then taking that data and then running the inference model. So running double-digit number of inference models in parallel. The solution that we provided is 2.6 times faster than the x86 solution. So it delivered, a pretty big gain in performance. So that kind of made it a no-brainer to to go ahead and utilize this solution, a step function increase in what they were able to provide in terms of services to the properties.
In terms of that x86 migration, in this case, are you seeing that in other customer engagements as well, in other applications?
We are. Yeah. I think that, when you look at the market, there's some small portion of the market where it's ARM native applications and code. Maybe it's Android applications. Maybe it's something in the automotive space where for many, many years, the code has always been ARM based. And that's a no brainer to run that stuff on an ARM based processor like Ampere processors. But there's a really large part of the market that has traditionally been x86 code. And the issues that market's facing is that running that x86 code on x86 CPUs isn't giving them the same gains that they are used to expecting over the last 10, 15, 20 years. Obviously, the Intel processors aren't as competitive on a gen-on-gen basis as they once were. And all of those processors are seeing large increases in power gen over gen. So it's starting to make it difficult to utilize x86 processors for a lot of power efficient use cases. So what I'm really seeing now is it's not that there's a ARM market and there's an x86 market. There's a market that needs high performance, power efficient processors. And that market is now moving their code from being x86 based to being ARM based. And the good thing about this is that the places where that's most common, the workloads where it's most common, these are a lot of cloud native workloads. These are a lot of workloads that use open source code. And so it's people running PyTorch. It's people running MongoDB. It's people running Nginx. All of that code has already been ported over to ARM. It has been for a long time. And so it's not a lot of extra work for somebody to utilize the ARM-based code versus the x86 code. It's just a one-time switch. And so increasingly, I'm seeing a lot of those traditional cloud and edge workloads moving off of x86 over to ARM, and it's running ARM code natively on ARM-based processors. And so it's really a seamless experience for the end user.
Let's go back to the Space Tech case study for a second. So this is an edge use case. And when you talk about modern workloads, AI workloads, it's usually a GPU conversation. But you guys are obviously CPU forward. You need GPU power and performance and presence in the data center, especially around training. But as you move out to the edge, talk to us about that landscape.
Yeah.
GPU versus CPU.
I would even cut it one step further. I think it's general purpose CPU on one end. It's GPU maybe on the other end, but just through a traditional lens. And then there's domain specific accelerators that probably sit somewhere in the middle. Now, today, certainly, AI training in data centers is the domain of GPUs. There's a decade plus of legacy there. These are big workloads that run for days, weeks, months, and big clusters. And so they look a little bit more like the GPU workloads of the past in supercomputing. But the training workloads are things that can happen in one place. They don't need to happen in 1,000 different places around the world because you train the model once and then you deploy the model. When you look at deploying that model or running these workloads, now it's a totally different problem statement. It's not running one workload for a really long period of time in one place. It's now running one workload that might run for, nanoseconds to milliseconds. So it needs really low latency. And then running that workload millions or billions of times in a short period of time. And those workloads have to sit really close to the end users that are getting the results because latency is really, really important. So now the GPU solution that sits in that big hyperscale data center training the model, that doesn't work in those places. It doesn't work for a number of reasons. It doesn't work because it can be trickier to deploy. It's just a more complicated system. And that's not what you need out of the edge. You need something that's much more compact and simple. It also tends to have a lot of thermal constraints. So it can be hard to cool some of those GPUs. They tend to consume more power. And also they can be significantly more expensive when you're looking for a big scale out solution that you can deploy anywhere. And so what somebody's looking for is really power efficient solution that's flexible, that can handle a lot of different workloads coming at it. It's not just running one workload for a long period of time. Keep in mind, these edge servers or edge devices aren't also just running AI inference all day long. They're also running all the other workloads that need to be provided in conjunction with inference. Maybe a bunch of databases, a web server. There's a bunch of caching pieces in there. I mentioned the video decode as well. So there needs to be a very flexible solution. And this is where CPUs are really good at this. CPUs are general purpose. They can run any workload, which means that whatever you throw at it, they're going to be able to handle. And so even when you don't know what the demand is from second to second, a CPU does a really good job of handling. CPUs also are good in this use case because it's a lot of data traffic, and minimizing the number of hops that data is making and keeping it in the CPU can be the lowest latency way to deliver these results. So, while a GPU can get the job done, it tends to do so a little less efficiently, more expensively, and a little less flexibly in these types of environments. Now, I did mention there's a piece in the middle where there is a need at times for different domain-specific accelerators, but that doesn't necessarily mean a GPU. That may mean a piece of AI acceleration hardware that's really, really good at large LLMs, or it could be a piece of acceleration hardware that's really good at computer vision, or like we see in NPUs and other types of DPU devices, it could be that it's really good at network traffic. And so I think that what we really see is you want really general purpose performance matched up with a very, very domain-specific acceleration. And that mix and match approach is a better solution.
When you sat down and started to hash out how this would look with the SpaceX folks, how much were they interested in the power efficiency story that you bring, and how much were they interested in the code base, the ecosystem around which they could create their solution?
Yeah, I think if you look at the requirements they had, the number one requirement was performance, with the number one constraint being power. And so, really their goal was deliver multiple X more performance, but still sit in the same power envelope. So that was the number one consideration. And then I think similar with many other people, I think that the code base and the overall ecosystem, that's table stakes. And so once we were able to prove that this code ran just as easily on these devices with only minor changes by moving to an ARM-based code base and using the right SDKs, then that became an easy part of the story. But at the end of the day, the reason why we're seeing this big migration away from x86 is because there's a need for more and more performance environments that are constrained, and x86 just doesn't get the job done. And when I say constrained environments, the obvious one is an edge where you clearly only have a limited amount of power. But frankly, hyperscale data centers are constrained today too. It's just a different order of magnitude.
Well, we're bumping up on time. We talked about workloads at the edge. We talked about workloads everywhere. Last question for you. What is your personal favorite AI application today?
Man, my personal favorite. Well, actually, I have young kids, so I would say that the two things they're most entertained by right now. So one is using ChatGPT to create stories. So they love that one. They love feeding in goofy stuff and seeing what ridiculous stuff comes back out again. So that's one that my kids really like. The other one is Stable Diffusion. So with some of the image generation models, I like this one for two reasons also. One, it's never been easier to create, what is essentially, stock images. Anything you come up with for a blog or something else, within seconds, you've got an image that kind of matches what you were thinking. But this is another one coming back to my kids. They also love, sending in crazy prompts and seeing what crazy image comes back again. I love I think it's the creativity and the way that the LLMs of today are able to kind of take the craziest things you come up with and then, turn them into whether it's writing, images, video instantly in ways that we never could have before. It kind of always had to sit in your imagination, and now they can kind of bring some of that stuff out and help you share it with other people.
Amazing times. We're fortunate to live in them, aren't we?
It is.
Well, Jeff Wittich, thank you so much for your time. Awesome conversation, and we look forward to having you on again in the future.
All right, perfect. Well, thanks, Brian. I really enjoyed it.